Hello everyone, this is the second video on chemical bonding. I am Dr. Sirajul Faizi. So I welcome you in my YouTube channel. So today in this video, I will focus on chemical bonding. This is second lecture. So I will start from dipole moments. Because in last video, I finished polarity of bond, and this is the part of polarity of bonds. So dipole moment, friends, is important parameter related to bonds. It is existence of partially charged negative and positive within a molecule. Mathematically, it is defined as the product of magnitude of charge on atom and distance between them. You can see chlorine-chlorine bond and HCl, there is a difference. In HCl, there is a partially positive and negative charge, but in CCl, there is no partially negative and positive charge. So dipole moment 0, but in case of HCl, there is some dipole moments. So dipole moment is represented by mu is equal to Q into R. SI unit of dipole moment is dBi, and 1 dBi is equal to 3.33 into 10 to the power minus 30 cm. Now friends, on the basis of dipole moment, covalent bond are two types. Polar bonds, molecules having values of dipole moment. Mu r is not equal to 0. But in case of water, you can see partially positive charge on hydrogens. Another hydrogen also a positive charge, and oxygen have partially negative charge. In ammonia, you can see in NF3 there is a opposite, means dipole moment in one direction more than another, so resultant of 3 NF bonds mu is equal to 0.24, so less dipole moments. Non-polar bonds, molecules having 0 dipole moments, mu r is equal to 0. So you can see carbon dioxide, carbon disulfide, BeF2, BF3, and methane, and carbon tetrachloride. Now friends, Fazan's rule. What is Fazan's rule? If covalent molecule shows partial ionic character, then ionic compound also possesses some covalent character, which depends on the following factor. Greater charge on cation, more is covalent character. A smaller cation or bigger anion shows greater covalent character. D elements forms more of covalent character compounds. I repeat, greater charge on cation, more is covalent character. A smaller cation or bigger anion shows greater covalent character. D elements form more of covalent character compounds. So, valence shell electron pair repulsion theory. Theory which gives and explains shapes of molecules. Main postulate of valence shell electron pair repulsion theory. Electron of valence shell of central atom participate to form bond. Electrons of surrounding atoms form bond with electrons of central atom. My friends, the central atom is linked to similar or different atom to get geometry. Bonded electrons and lone pair electrons repel each other to attain a shape having minimum repulsion and maximum stability. So repulsion, lone pair greater than lone pair greater than bond pair. So lone pair LP and bond pair BP. Now shape of molecules without lone pair. Linear, for example BF2, BeCl2, HgCl2. Trigonal planar, AlCl3, SO3. Tetrahedral, SiF4 and ammonium ion. Trigonal bipyramidal, PCl5, PF5, antimony pentafluoride, arsenic pentafluoride, and octahedral SF6. Shape of molecules with lone pair. Bent V-shapes, SO2, O3, SnCl2, pyramidal, PCl3, NCl3, NF3, PS3, S3O+, bent H2S in NH2 minus, seesaw SF4, T-shaped ClF3, linear XeF2 I3 minus, Br3 minus, ICl2 minus, square pyramidal ClF5, IF5, Brf5, and square planar XeF4. Now friend, valence bond theory, VBT. According to VBT, when atoms are brought close to each other, they form a stable molecule with a bond. For example, when two unstable hydrogen atoms are far away, then force of repulsion and force of attraction are negligible. When they come closer at some minimum distance, bond length, force of attraction is high and force of repulsion is minimum. Case 3. On further decreasing distance between them, attraction is too high, but repulsion also becomes so high which makes the molecule unstable. So intermolecular distance, bond length, potential energy, you can see in this picture. So E is equal to negative, release exothermic, and positive, absorb endothermic. So postulates and silent future of valence bond theory. Electron present in valence shell of central and surrounding atom participate. Only unpaired electron of valence shell participate but not lone pair. Unpaired valence electrons overlap or forms bond with unpaired electrons of central metal atom but with the opposite spin. These bonds formed are of two types. So sigma bonds and pi bonds. What is the sigma bond? Sigma bond atomic orbitals overlap on internuclear axis INA and pi bond overlapping perpendicular to INA. Sigma bond extent of overlapping is more, therefore a stronger bond. Pi bond less, hence weaker. Sigma bond can exist independently. Pi bond only with sigma bond. Sigma bond head-on overlapping. Pi bond sideways overlapping. Sigma bond exists between SS, SP and PP. Pi bonds only PP. So only PP and others. Atom approach each other. You can see overlap regions in between hydrogen. In case of HCl, 1s and 3p. In case of CCl, ClCl, 3p, 3p. So you can see in the pi bonds sidewise overlapping. So drawbacks of valence bond theory, VBT. According to VBT, only unpaired electrons are paired. Therefore, the simplest hydrocarbon which exists in nature should be CH2, but CH2 does not exist and is highly unstable, and the hydrocarbon which exists is CH4. Similarly, according to valence bond, instead of BF3 or BH3, only BF and BH should exist, and as it has one unpaired electrons, and B should not form any compound as it doesn't have any unpaired electrons. So hybridization. So what is hybridization? It is the mixing of atomic orbital of similar energies to get new stable hybridized orbital of same energy and shape. What is the silent features of hybridizations? Atomic orbitals of similar energy can participate. Number of atomic orbitals combining gives same number of hybrid orbitals. Paired, unpaired and vacant orbitals can participate. And a number of atomic orbitals combining gives same number of hybrid orbitals. Paired, unpaired and vacant orbital can participate. And the next important point is hybrid orbitals HO forms stronger and stable bonds, and these hybrid orbitals repel to give proper geometry. Now friends, important conditions for hybridizations. Atomic orbital with similar energy gives participates, not necessary for excitation of electrons, not necessary only unpaired electron participate, and electrons in last and second last shell also can participate. So types of hybridization: sp3, sp2, sp, sp3d, sp3d2. Now friends, sp3 hybridizations. When 1s and 3p, px, py, pz, atomic orbital of similar energy combine, they form 4 new stable hybrid orbitals which having the same energy and shape. These 4 hybrid orbitals form sigma bond and each having 25% s character and 75% p character. These 4 hybrid orbitals repel each other to give tetrahedral geometry with 109.28 degree angles. For example, alkane, methane, ammonia, ammonium, water and S3O plus etc. Formation of sp3 hybrid orbitals. You can see S, Px, Py, Pz combine to generate 4 sp3 orbitals which are represented as the set. Now, sp2 hybridizations. 1 s and 2 p orbitals participate to give 3 new sp2 hybridized orbitals. Each possesses 33% s character and 67% p character, and they repel each other to give trigonal planar geometry with 120 degree bond angles. Example, alkenes C2H4, BH3 and BF3. You can combine to generate 3 sp2 orbitals, and this is the sp hybridizations. 1s and 1p orbital participate to form 2 new hybridized orbital, each having 50% s character and 50% p character. Both hybridized orbitals repel each other to give linear shape with bond angles 180 degree. Since it has maximum s character, hence has maximum electronegativity. So s orbital and p orbital, you can see 2 sp hybrid orbitals and sp hybrid orbitals shown together. So sp3 hybridizations. 1s and 3p and 1d orbitals of same shell participate to give sp3d hybrid orbitals with trigonal bipyramidal shape with bond angles 90 degree and 120 degree. For example, pf5 and pcl5. So p ground state 1s2, 2s2, 2p6, 3s2, 3p3. P excited state 1s2, 2s2, 2p6, 3s1. So sp3d you can see. So now have 5 hybridized orbital which form 5 sigma bond. 3pCl bond form trigonal planar shape with 120 degree bond angles and are called equatorial bond, which are short and strong. 2 PCl are placed perpendicular, which experience greater repulsion, hence are long and weak and called axial bonds. So the overall shape is trigonal bipyramidal. PCl5 is thermally unstable and gives PCl3 and Cl2 gas on heating because its 2 axial PCl bonds are weak. So PCl5 solid, on heating it gives PCl3 and Cl2. Now friend, sp3d2 hybridizations. 1s, 3p and 2d orbitals of same shape participates and give sp3d2 which octahedral shapes having all bonds angle 90 degree. You can see SF6 ground state, electronic configuration 1s2, 2s2, 2p6, 3s2, 3p4, excited state 1s2, 2s2, 2p6, 3s1, 3p3, 3d2, sp3d2. So molecular orbital theory. Molecular orbitals, it is the shape around the nuclei of molecules where the probability of finding electron is maximum. What is the silent feature of MOT? Molecular orbitals gives the electron probability distribution around a group of nuclei, just as an atomic orbital gives the electron probability distribution around a single bond. So my friends, I hope I will make molecular orbital theory video in my next video. So if you like this video, then subscribe my channel, and thanks for watching. And further, I suggest, I already uploaded one video on basic of chemical bonding. So please go through that video and then see and this video, and then wait for the next video. So friends, I think you can also share this video in your friends account. Thanks for watching.